So let's continue on. We will talk about some oxidation reactions of alkenes next. Okay, so oxidation reactions. Uh, there are three different kinds that we will be talking about here. The first one that we're going to talk about here is the epoxidation. Okay, and what the epoxidation does is it converts the alkene into an epoxide. Now we'll learn more about the chemistry of epoxides later. And the reagent that is needed for doing this reaction, okay, the reagent is a peroxy acid. Now, the most common one you may have seen is MCPBA, which is metachloroperoxybenzoic acid. So essentially what happens is if we start with the alkene that we've been using as an example, and if we subject it to an epoxidation, MCPBA, and common solvent is chloroform, then we will convert this alkene into an epoxide. Okay, this plus its enantiomer is what we're going to make. So you add this the oxygen, and it's a three-membered ring that's formed. So it's an ether. An epoxide is basically a three-membered ring containing an oxygen. Okay, so that's the epoxidation reaction. A second oxidation that you can do on alkenes is sorry, instead of just saying it syn, I'm going to call it a dihydroxylation. Okay, now we're going to learn about two types of dihydroxylations here. So what this reaction does is it converts an alkene into an alkane diol, or better, we should be calling it a vicinal diol. This is when you have two hydroxyl groups on adjacent carbons. Okay, we can do this two ways, and it gives us two products actually. So if we start with the alkene, and if you react it first with a peroxy acid, sorry, let's say MCPBA, and second you do a hydrolysis, an acidic hydrolysis of that ether, then you will get a diol, and this diol would be an anti-diol. Okay, so we get the anti-diol because the two hydroxyl groups are facing in opposite directions. The second one is where you start from that alkene, and you either do a reaction with osmium tetroxide followed by reaction with a peroxide, or sometimes you would see that it is also sodium sulfite. One possibility, and the product here is going to be a syn diol. So this is a syn diol. Both hydroxyl groups are pointing in the same direction. So you will get this plus its enantiomer. So we can write plus minus actually for both of these to say that you get a racemic mixture here. Okay, so the second reaction which does this same thing, okay, or the second set of reagents that does this is potassium permanganate, and you want this to be dilute KMnO4, and it has to be cold in presence of a base like hydroxide. So when you have some hydroxide, it still gives you the syn dihydroxylation product. Okay, so there are two ways of doing a dihydroxylation, and you would get an antidiol or a syn diol depending on the reagents that you choose. Now, the third kind of an oxidation that you can do on an alkene is the ozonolysis. Okay, and what ozonolysis does is it would convert, actually it will break the carbon-carbon double bond. Okay, it will break this carbon-carbon double bond for you to give carbonyl compounds as products. So by carbonyl compounds we mean aldehydes and or ketones. Okay, that's what we imply. So essentially, if we have the alkene, again, let me use the alkene that we've been using so far. If we take this and if you do an ozonolysis, this is done in two steps again. First is the reaction with ozone, and this reaction is done at low temperatures. And second, you kill this reaction using some zinc, or you could use dimethyl sulfide. Either one is fine. And when you do it, it is going to break open that double bond. Okay, and what happens is it adds an oxygen, to both ends, to those carbon atoms. So if I look at this molecule, I have a ring which was 1, 2, 3, 4, 5 carbons. So I can draw 1, 2, 3, 4, 5 carbons. Carbon number 1 was part of the double bond, and now carbon number 1 should have a double bond O on it. Carbon number 5 was part of the double bond, so this is 1, 2, 3, 4, and 5. Carbon number 5, I'm going to write at the top here. Okay, and 5 was also part of the double bond, and there should be a double bond O over there. And on 5, there is a hydrogen here. So I'm going to draw that hydrogen here, not required, but I'm going to draw that in. And so we've got an aldehyde on that end. And on carbon number 1, there was a methyl group attached. So I'm going to include a methyl group over there. So that's the product that I get. Okay, so we got a ketone and an aldehyde from that molecule. Now, this is a cyclic alkene. That's why we got a product where the aldehyde and the ketone are part of the same molecule. But let's say if we started with another alkene, let's just use this as an example. And if we did the same reaction, so ozonolysis at low temperature, followed by dimethyl sulfide, let's say, the double bond is going to break and it's going to add an oxygen on either end. So the product that I will get, or the products that I will get, would be double bond O here. So I get a ketone, and then 1, 2, 3 carbons. So 1, 2, 3 carbons, double bond O. Now, the molecules that I've chosen so far, they both resulted in an aldehyde and a ketone. It does not have to be that way. So imagine if I had another methyl group here on that carbon, then there would be that methyl group here. So that means my products are going to be 2 ketones. So the product, whether you get a mixture of 2 aldehydes, 2 ketones, or a ketone and aldehyde, really depends on your alkene that you start with. Okay, so those are all the oxidation reactions of alkenes. Now, other than this, we are going to talk about a reduction of an alkene, very simple. And a reduction reaction here that we're going to talk about is the hydrogenation. And what this does is it would convert the alkene to an alkane. And this reaction is done using some catalyst. Okay, you use a catalyst, let's say platinum, and you use hydrogen gas. So you could use platinum or palladium, any of those metals, and then use hydrogen gas for doing this reaction. So if we did the reaction on the molecule that we were using, if I did hydrogen gas with platinum as a catalyst, my product is going to be the alkane. That's possible. You add the hydrogens to that double bond. So that I believe is sort of a comprehensive review of almost all the reactions of alkenes that we have seen. In the next slide, we will in the next video or the slide, we will continue on with some reactions of alkynes, and then we will continue on from there. Okay. Now that we've completed the synthesis and the reactions of alkenes, we'll start talking about alkynes. But before we do that, I also want to draw some sort of a connection between what we've done so far. Not all the reactions, but at least some of the reactions. Okay, so what we've seen so far is that you can convert alkanes into alkyl halides. This is using the free radical halogenation reaction. Alkyl halides can be converted into alkenes by doing E2. So this is free radical halogenation. This is E2. Now we are referring to E2 specifically. This could be E2 or E1, but we're referring to E2 specifically because E1 always competes with SN1. So you can convert alkyl halides into alkenes. And with alkenes, one reaction of alkenes that we learned is that when you halogenate them in a non-coordinating solvent, you can convert them into alkyl dihalides. Okay, and alkyl dihalides is important. Okay, so we'll continue from there, but I also want to connect some other dots here while we are at it. Now, recollect that alkenes, these can be converted back into alkyl halides by hydrohalogenation. Okay, which is the addition of HX. And by choosing the Markovnikov or the anti-Markovnikov hydrohalogenation, we can get either the more substituted alkyl halide or the less substituted alkyl halide. So there are possibilities here. And the same applies starting from the alkyl halide. From the alkyl halide, when you're making alkenes, you can make either the more substituted alkene using a strong base, or you can make the less substituted alkene using a bulky base. Okay, so there are various possibilities here, but these reactions are sort of related. That is what I wanted to point out. Okay, now since we are talking about alkynes here, alkynes are actually synthesized from alkyl dihalides, or at least one of the routes to doing it. Now, I want to add some detail here. When you halogenate an alkene, the alkyl dihalide that you get is a vicinal dihalide. Okay, but vicinal dihalides can be converted into alkynes using E2 again. Okay, so by using an elimination reaction. So we'll talk about that. So going to the specifics here. Okay, so synthesis of alkynes, which is the topic. Okay, so the first route to synthesizing alkynes is starting from a vicinal dihalide. So if we have X and X, this is a vicinal dihalide, and this is what you will get from alkenes. Okay, that's the vicinal dihalide that you get when you do a halogenation on an alkene. So from the vicinal dihalide, if you react the vicinal dihalide with a strong base under forcing conditions, so usually a good base that you can use here is sodium amide. So sodium amide, and this is used in excess, okay, because you have to remove two halogens here. So we use excess of the sodium amide with heat, and you quench this reaction with water later. You will get an alkyne from this. Okay, keep track of your carbon count, which is important. So apart from the R group, I had 2 carbons here, and notice how there are 2 carbons here. Okay, so we get the H. So we get an alkyne. Now the mechanism of how this reaction works is again beyond the scope of what we are doing here. We're just reviewing some of these reactions. Okay, so vicinal dihalides will give you an alkyne. Now your alkyl dihalide does not have to be a vicinal dihalide. If you have a geminal dihalide, which means both halogens are on the same carbon atom. Okay, this is a geminal dihalide. Even a geminal dihalide can be reacted with a strong base under forcing conditions to give you an alkyne product. Okay, again you quench with water here. So you can make the alkyne from a geminal dihalide also. Now both of these alkynes that we made here, these because of their structure, these are terminal alkynes, which basically means that the double bond, terminal means that the double bond is at the end of a carbon chain. Okay, so that's the last carbon. That's where the double bond, the triple bond is at the end of a carbon chain. The triple bond is at the end of that carbon chain, so that's why they're called terminal alkynes. Okay, so those are 2 methods of synthesizing alkynes, starting from either a vicinal dihalide or a geminal dihalide. The vicinal dihalide, as I said earlier, is obtained from alkenes. So that's the connection to alkenes here. The geminal dihalide, these are not made from alkenes. Actually, if you take an alkyne and you add HX to it, if you do a hydrohalogenation on it, two equivalents, then you will get a geminal dihalide. So this is a hydrohalogenation of alkynes that gives you the geminal dihalide. Now, once you've made the terminal alkyne, you can always convert it into a longer chain alkyne by doing an alkylation. So you can deprotonate the terminal alkyne using sodium amide, and then if you add another alkyl halide to it, then this would give you an alkyne with more number of carbon atoms because you would have added this R prime to it. So you can convert that terminal alkyne into what is now an internal alkyne. Okay, so these are some syntheses of alkynes. Now that we've talked about the synthesis of alkynes, let's continue on with the reactions of alkynes. The reactions of alkynes are called addition reactions again, similar to alkenes. And whatever the reaction, and for the most part, alkynes just do the reaction twice over, whatever the alkene did. Now to walk you through these reactions, I'm going to use a simple alkyne here. And a simple terminal alkyne is what I'm going to use. So let's say we have an alkyne which is this molecule here. Okay, so if we take this molecule and if we do a hydrohalogenation, which is the addition of HX, now since we have two pi bonds here, I'm going to use an excess of the HX because I have two bonds. So you need at least two equivalents. So if you do that, then your product from this reaction is going to be a molecule which is a geminal dihalide. So I sort of mentioned this during the synthesis of alkynes. So we get a gem dihalide. Okay, and gem dihalides can also be converted into an alkyne using an E2 reaction, as we saw earlier. So that's the halogenation reaction. Compare this to the the hydrohalogenation reaction. Compare this to a hydrohalogenation of an alkene. That would give us an alkyl halide. Okay, similarly, if we have this alkyne, and if I do a halogenation on this, again, because there are two pi bonds, I'm going to use an excess of the halogen. Our product is going to be an alkyl tetrahalide. With an alkene, we got an alkyl dihalide, and now you get an alkyl tetrahalide. Okay, that will be our product. Now you can do hydrogenation and reduction on alkynes, very similar to what we did with alkenes, but you can do more here. Okay, so if we do a hydrogenation on a terminal alkyne, like the one that we were using, so if I take this alkyne and if I do a hydrogenation, so if I use H2 gas with platinum catalyst, what I will get is the alkane. So the alkyne is converted into an alkane. Now, this reaction, sort of notice how it gets rid of all the functional groups. because you started with an alkyne which had this functional group in it, and now you have an alkane where there is which is lacking functionality. So you can do this reaction in a controlled manner by using a poison catalyst, which could be hydrogen gas, and you can use Lindlar's catalyst. Again, the details of what this catalyst is, those can be found in the Alkynes chapter. So you can use Lindlar's catalyst, or you can even use nickel boride actually. And what this does is it stops the reaction at the alkene stage. Okay, so you can go from the alkyne to an alkene and stop the reaction over there. Now it turns out in this particular case we were using terminal alkyne. If I had an internal alkyne, so let's say if I started with an alkyne like this, now this is an internal alkyne, and if I did the reduction using Lindlar's catalyst, or sorry, the hydrogenation reaction using Lindlar's catalyst or nickel boride, then the product that I get, or the alkene that I get as my product, is going to be a cis alkene. So my alkene is going to be a cis alkene. Okay, so we get a cis alkene as our product using this reduction, using this hydrogenation reaction with a poison catalyst. Now, so if we get the cis alkenes this way, how could we convert the alkyne into a trans alkene? For doing that, we can do this reaction using sodium and liquid ammonia. So if I have that, and if I react this with sodium and ammonia liquid, this reduction gives us the trans alkene. So that means I can, again, by choice of reagent, we can control which product we get. Okay, so starting from an internal alkene. Now, the cis and the trans matters, sorry, starting from an internal alkyne. The cis and the trans matters only if you're starting from an internal alkyne. Because if we start from a terminal alkyne, if I do sodium and ammonia liquid on this, my product is going to be this alkene, which is not very different, or which is not different from what I get when you use the poison catalyst. So I get the same alkene. So it is for the internal alkynes that this hydrogenation with the poison catalyst versus a reduction reaction matters, because you get the cis or the trans alkene. Now moving on to some oxidation and hydration reactions. You can do hydration on alkynes. So again, choosing this alkyne, you do a hydration on this. You could use mercuric sulfate with dilute sulfuric acid. Okay, you could put that down, or you could just put H3O plus. Okay, this is a hydration. Your product in this particular reaction is a ketone, and I want to highlight certain carbons here. So when this transformation is going on for this internal carbon here of the terminal alkyne is what becomes the carbonyl carbon in the product. So that's the hydration. So the hydration of alkynes gives you the ketone. Now this is a terminal alkyne. If this reaction were done using an internal alkyne, then you would have two possibilities for the ketone product. If I did the same thing using an internal alkene, I'll get two products, because now we will get this ketone plus I will get that ketone, okay, where this carbon became the carbonyl carbon, or alternatively the other carbon became the carbonyl carbon. So you get a mixture of products here. These are both hydration reactions. One is of a terminal alkyne, the other one is an internal alkyne. Okay, now when you do a hydroboration oxidation, and this reaction is more relevant for terminal alkynes. When you do the hydroboration oxidation, so let's say if you reacted with BH3THF and second H2O2 with hydroxide. Now, the borane that's used for this reaction is usually like a 9-BBN or a dicyanyl borane. I'm just putting borane THF as a very simple example here. Okay, when you do that, your product in this particular case is going to be a carbonyl, which is an aldehyde. Okay, so we are getting ketones as products there, and now you get an aldehyde as a product if you did a hydroboration oxidation. Now, if you do a hydroboration oxidation on an internal alkyne, you will again get ketones. Okay, so for this internal alkyne, whether you did that, the hydration, or you do 1BH3.THF and then 2H2O2 with hydroxide, your products are going to be the same. You're going to get those two ketones as your products, irrespective of whether it's a hydration or a hydroboration oxidation. So it's for the terminal alkynes that you actually see a difference. A terminal alkyne upon hydration would give you a ketone product, and a terminal alkyne upon hydroboration oxidation would give you an aldehyde product. Okay, so that's where the difference lies. Now, coming to ozonolysis, when you do ozonolysis on an alkyne, and I'll use an internal alkyne here, when you do ozonolysis, so the conditions are similar to what we saw in case of alkenes. The only difference is, here, you quench this by adding some water. Okay, and when you do that, again, you end up cleaving that triple bond, and what you get as products are two carboxylic acids. Okay, so the carbons that were part of the triple bond, they're both converted into a carboxylic acid functional group. You can count the number of carbons and make sure that we have the right number of carbons here. Okay, so those, I would say, are like some of the most important reactions of alkynes that you've encountered in the first semester of organic chemistry. So now that we've covered almost all the reactions, in the next set of videos, we'll start looking at some synthesis. How do we use these reactions, a combination of these usually, to go from a given starting material to a desired product? How do people use this in industry to make molecules that they want? Okay, so that is what we are trying to do in the next set of videos.